Software errors. We usually think of hardware faults as being random and independent from each other. One machine is failing does not imply that another machine is going to fail. There may be weak correlations, for example, due to a common cause, such as the temperature in the server rack. But otherwise, it is unlikely that a large number of hardware components will fail at the same time. Another class of fault is a systematic error within the system. Such faults are harder to anticipate, and because they are correlated across nodes, they tend to cause many more system failures than uncorrelated hardware faults. Examples include a software bug that causes every instance of an application server to crash when given a particular bad input. For example, consider the leap second on June 30, 2012, that caused many applications to run simultaneously due to a bug in the Linux kernel. A runaway process that use up some shared resources, CPU time, memory disk space, or network bandwidth. Service that the system depends on that slowdown becomes unresponsive or start returning corrupted responses. Cascading failures, where small faults in one component triggers a fault in another component, which in turn trigger further faults. The books that cause this kind of software fault often lie dormant for a long time until they are triggered by an unusual set of circumstances. In those circumstances, it is revealed that the software is making some kind of assumptions about its environment, and while that assumption is usually true, it eventually stops being true for some reason. There is no quick solution to the problem of systematic faults in software. A lot of small things can help. Careful thinking about assumptions and interactions in the system through, uh, through testing, process isolation, allowing process to crash and restart, measuring, monitoring, and analyzing system behavior in production. If a system is expected to provide some guarantee, for example, in a message queue, that the number of incoming messages equals the number of outgoing messages, it can constantly check itself while it is running and raise an alert if a discrepancy is found. Human errors. Human design and build software systems, and the operators who keep the system running also are human. Even when they have the best intentions, humans are known to be unreliable. For example, one study of large internet services found that configuration errors by operator were the leading cause of outage, where hardware faults, server or network, played a role in only 10-25% of outages. How do we make our system reliable in spite of unreliable humans? The best system finds several approaches. Design system in a way that minimizes opportunities for error. For example, well-designed applications, APIs, and admin interfaces make it easy to do the right thing and discourage the wrong thing. However, if the interfaces are too restrictive, people will work around them, negating their benefit. So this is a tricky balance to get right. A couple places where people make the most mistakes from the places where they can cause failures. In particular, provide fully featured no production sandbox environment where people can explore and experiment safely using real data without affecting real users. Tests truly at all levels, from unit tests to whole system integration tests and manual tests. Automated testing is widely used, well understood, and especially valuable for covering corner cases that rarely arise in normal operations. Allow quick, easy recovery from human errors to minimize the impact in the case of a failure. For example, make it fast to roll back configuration change, roll out new code gradually, so that any unexpected bug affect only a small subset of the user, and provide tools to recompute data in case it turned out that the whole computation was incorrect. Set up detailed, tailored, and clear monitoring, such as performance metric and error rate. In other engineering disciplines, this is referred to as telemetry. Once a rocket has left the ground, telemetry is essential for tracking what is happening and for understanding failure. Monitoring can show us early warning signals and allow us to check whether any assumptions or constraints are being violated. When a problem occurs, metrics can be invaluable in a diagnosis the issue. Implement good management practices and training, a complex, important aspect and beyond the scope of this book. How important is reliability? Reliability is not just for nuclear power station and air traffic control software. More mundane applications are also expected to be reliable. Bugs in business applications cause loss, productivity, data risk if figures are reported incorrectly. An outage of e-commerce site can have huge costs in terms of lost revenue and damage to reputation. Even in non-critical applications, we have a responsibility to our users. Consider a parent who store all the pictures and video of their children in your photo application. How would they feel if that database was suddenly corrupt? Would they know how to store it from a backup? There are situations in which may choose to sacrifice reliability in order to reduce development costs when developing a prototype product for an unproven market, or operational costs for a service with a very narrow profit market. But we should be very conscious of when we are cutting corners. Scalability. Even if a system is working reliable today, that doesn't mean it will necessarily work reliable in the future. One common reason for degradation is increasing loads. Perhaps the system has grown from 10,000 concurrent users to 100 concurrent users, or from 1 million to 10 million. Perhaps it is processing much larger volume of data than it did before. Scalability is the term we use to describe a system's ability to cope with increased load. Note, however, that it is not a one-dimensional label that we can attach to a system. It is meaningless to say X is scalable or Y doesn't scale. Rather than discussing scalability meaning, consider questions like if the system grows in a particular way, what are our options for coping with this growth? And how we can add computing resources to handle the additional load. Describing load. First, we need to succinctly describe the current load on the system. Only then we can discuss growth questions. What happens if our load doubles? Load can be described with a few numbers, which we call load parameters. The best choice of parameters depend on the architecture of your system. It may be requests per second to a web server, ratio of reads write in a number, as active user in a chat room, hit rate on a cache, or something else. Perhaps average case is what matters for you. Perhaps your bottleneck is dominated by a small number of extreme cases. To make this idea more concrete, let's consider Twitter as an example, using data published in November 2012. 16. Two of Twitter's main operations are post tweet, the user can publish a new message to their follower, 4.6K requests per second on average, over 12K requests per second at peak. On timeline, the user can view tweets posted by the people they follow, 300K requests per second. Simply handling 12,000 writes per second, peak rate for posting would be fairly easy. However, Twitter scaling challenge, not primarily due to tweet volume, but due to fan out. Each user allows many people, and each user is followed by many people. There are broadly two ways of implementing these two operations. Posting tweet simply insert the new tweet into a global collection of tweets when a user requests they hunt timeline. Log up all the people they follow, find all the tweets for each of those users and merge them, sorted by time. In a relational database, figure 1/2, you could write a query such as this. A term borrowed from electronic engineering, Fanout is a term borrowed from an electronic engineer where it describes the number of logic gate inputs that are attached to another gate output. The output needs to supply enough current to drive all the touch inputs in transactions processing system. Use use it to describe the number of requests for the service that we need to make in order to serve one incoming request. Maintaining cache for each user home timeline, like a mailbox of tweet for each receiving user. In figure 1/3, when a user posts a tweet, look up all the people who follow that user and insert the new tweet into each of their home timeline cache. The request to read the timeline is then cheap because its result has been computed ahead of time. Figure 1/2 simple relational schema of implementing a Twitter home timeline. Figure 1.3 Twitter data pipeline for delivering a tweet to follower with low parameters as November 2012. The first version of Twitter used approach 1, but the system struggled to keep up with the load of home timeline queries. So the company switched to approach 2. These work better because the average rate of published tweets is almost 2 orders of the magnitude lower than the rate of home timeless read. And so, in this case, it's preferable to do more work at write time and less at read time. However, the downside approach too is that posting a tweet now requires a lot of extra work. On average, a tweet is delivered to about 75 followers, so 4.6k tweets per second become 345k, 345k write per second to a home time and cache. But this average hides the fact that the number of followers per user varies widely. Some users have over 30 million followers. This means that a single tweet may result in over 30 million writes to home timeline. Doing this in a timely manner, Twitter tries to deliver tweets to followers within 5 seconds. It's a significant challenge. In the example of Twitter, the distribution of followers per user may be weighted by how often those users tweet is a key load parameter for discussing scalability, since it determines the fan out load. Your application may have very different characteristics, but you can apply similar principles to reasoning about its load. The final twist of the Twitter anecdote, now that approach 2 is robust implemented, Twitter is moving to a hybrid of both approaches. Most users, most users tweet continue to be funneled out to home timeline at the time when they are posted, but a small number of users with a very large number of followers, sample celebrities, are expected from this fan out. Tweets from any celebrity that user may follow are fetched separately and merged with that user home timeline when it is read, like an approach 1. This hybrid approach is able to deliver consistent good performance. We will revisit this example in chapter 12 after we have covered some more technical ground. Describing performance. When you have described the load on your system, you can investigate what happened when the load increased and look at it in 2 ways. When you increase load parameter and keep the system resource, CPU, memory, network bandwidth, unchanged, how is the performance of your system affect? When you increase load parameter, how much do you need to increase the resource if you want to keep performance? Both questions require performance number. So let's look briefly at describing the performance of a system. In a batch processing system such Hadoop, we usually care about throughput, the number of records we can process per second, of the total time it takes to run a job on a dataset or the center size. In online system, what's usually more important is the service response time. That is, the time between a client sending a request and receiving a response. Certain size. In an idea where the running time of a batch job is the size of the dataset divided by the throughput. In practice, the running time is often longer due to skew, data not being spread evenly across worker processes, and needing to wait for the slowest task Latency and response time. Latency and response time are often used synonymously, but they are not the same. The response time is what the client sees, beside the actual time to processing the request. Service time. It includes network delays and queuing delays. Latency is the duration that a request is waiting to be handled, during which is latent, awaiting services. Even if you only make the same request over and over again, you will get slightly different response time on every try. Practice in a system handling a variety of requests, the response time can vary a lot. We, therefore, need to think of responses time not as a single number, but as a distribution of value that you can measure. In figure 1/4, each gray bar represents a request to a service, and its a I show how long that request took. Most requests are reasonably fast, but there are occasional outliers that take much longer. Perhaps the slow requests are intrinsically more expensive, example because they process more data. But even in a scenario where you have think all requests should take the same time, you get variations. Random additional latency could be introduced by a context switch to a background process, the loss of the network packet, and TCP retransmission, a garbage collection pause, page fault forcing a read from disk, mechanical vibration in the server rack, or many other causes. Figure 1/4, illustrating mean and percentage response time for a sample of 100 requests to a service. It is common to see the average response time of the service report. Strictly speaking, the term average doesn't refer to any particular formula, but in practice, it is usually understood as the arithmetic mean. Given n values, add up all the values and divide by n. However, the mean is not a very good metric if you want to know your typical response time, because it doesn't tell you how many users actually experience that delay. Usually it's better to use percentile. If you take your list of response times and sort it from fast to slowest, then the median is the halfway point. For example, if you median response time is 200 milliseconds, that means half your requests return in less than 200 milliseconds, and half your requests take longer than that. This made the median a good metric if you want to know how long users typically have to wait. Half of user requests are reserved in less than the median response time, and the other half take longer than the median. Median is also known as the 50th percentile, and sometimes abbreviated as P50. Note that the median refers to a single request. If the user makes several requests over the course of a session, or because several results are included in a single page, the probability that at least one of them is slower than the median is much greater than 50. In order to figure out how bad your outliers are, you can look at higher percentage. 95, 98, 99.9 percentile are common. Abbreviated P95, P99, P999. They are the response time threshold at which 95%, 99%, or 99.9% requests are faster than the particular threshold. For example, if the 95 percentiles performs response time is in 1.5 seconds, that means 95 out of 100 requests takes less than 1.5 seconds, and 5 out of 10 requests take 1.5 seconds or more. This is illustrated in figure 1/4. High percentage of the response time, also known as tail latency, are important because they directly affect user experience of the service. For example, almost a described response time requirement for internal services in terms of 99.9 percentiles, even though it is only affect 1 in 100 requests. This is because the customer with the slowest requests are often those who have the most data on their account, because they have made many purchase. That is, they are the most valuable customer. I think it is important to keep those customers happy by ensuring the website is fast for them. Amazon has also observed that 100 milliseconds increase in response time reduce sales by 1%. And others report that a 1 second slowdown reduce a customer satisfaction metrics by 60%. On the other hand, optimizing the 99.99 percentile, lowest one in 10,000 requests, was deemed too expensive and not to yield enough benefit from Amazon purpose. Reducing response time at very high percentage is difficult because they are easily affected by random events outside of your control, and the benefits are diminishing. For example, percentages are often used in several level objects, SLO, and service level agreements, SLAs, contracts that define the expected performance and availability of a service. An SLA may state that the service is considered to be up if it has a median response time of less than 200 milliseconds and 99 percentile under 1 second. If the response time is longer, it may as well be down, and the service may be required to be up at least 99.9% of the time. This metric sets expectation for clients of the service and allow customers to demand a refund if the SLA is not met. Queuing delays often account for a large part of the response time, a high percentage. As a server can only process a small number of things in parallel, limited for example by its number of CPU cores, it's only take a small number of load requests to hold up the processing of subsequent requests, an effect sometimes known as head of line blocking. Even if those subsequent requests are fast to process on the server, the client will see a slow overall response time due to the time waiting for the prior request to complete. Due to this effect, it is important to measure response time on the critical side. When generating loads artificially in order to test the scalability of a system, the load generating client needs to keep sending requests independently of the response time. If the client waits for the previous request to complete before sending the next one, that behavior has the effect of artificially keeping the queues shorter in the test than they will be in reality, which skew the measurement. Percentiles in practice. High percentiles become especially important in backend services that are called multiple times as part of serving single user request. Even if you made the call in parallel, user requests still need to wait for the slowest of the parallel call to complete. It takes just one slow call to make the entire end user request slow, as illustrated in figure 1/5. Even if only a small percentage of backend calls are slow, the chance of getting a slow call increase if an end user request require multiple backend calls. And so high proportion of end user requests end up being slow and effect known as latency amplification. If you want to add response time percentage to the monitoring dashboard for your service, you need to efficiently calculate them on an ongoing basis. For example, you may want to keep a rolling window of responses time of requests in the last 10 minutes. Every minute, you calculate the median and various percentage of the values in the windows and plot those metrics on a graph. The native implementation is to keep a list of response time for all requests within the time window and to sort that list every minute. If that is too inefficient for you, there are algorithms that can calculate a good approximation of percentile and minimal CPU and memory cost, such as forward decay, EDGs, and HDR histogram. Beware that averaging percentiles, example to reduce the time resolution or to combine data from several machines, is mathematically meaningless. The right way of aggregating response time data is to add the histogram. Figures 1 Like 5, when several backend calls are needed to serve a request, it takes just a single slow backend request to slow down the entire end user request.